Okay, here's our quick look at Chapter 18, which covers organic chemistry. Now, guys, organic chemistry is a huge, huge field, quite possibly the largest field in chemistry. My notes here tell you that over 95% of all known chemical compounds are based on carbon. That makes them organic chemicals. So organic chemistry, we can't cover too much in this chapter. We'll just give you a little taste of it. If you end up going into chemistry, you take a whole year's worth of organic chemistry, and even then you barely scratch the surface in that whole year. But I do want you to become somewhat familiar with organic structure and some functional groups. So here we go. Organic structure. We show structures of molecules, of course, with Lewis structures. This is an example of a Lewis structure. You have double bonds, single bonds, lone pairs. Organic chemistry, I haven't quite told you yet, organic chemistry is the chemistry of this element, the chemistry of carbon. This is the most important element on the periodic table if you're an organic chemist like me. So, what do you got to know about organic structure here? All carbon atoms want to have 4 bonds. They always get 4 bonds. You can do it different ways. You can have a carbon atom with 4 single bonds. You can have, look at this guy here, he's got a double bond and 2 singles. You could have, like if you look at this carbon, he's got his 4 bonds from a triple and a single. Here you have a double bond to oxygen, single bond to oxygen, single bond to another carbon, so this carbon has 4 bonds. Now, the other big thing to know in organic chemistry, remember the one element that never gets an octet, the one element that can only ever make 1 bond is hydrogen. So in all the organic structures you see, the hydrogen atoms are always going to be on the outer periphery of that structure. Notice how the hydrogens are on the outside of it. You can have oxygen bonded to carbon, which could go on and on and on. But once you get to a hydrogen, you can't go anywhere. In our model kit here, you notice the hydrogen atoms only have one little peg because all a hydrogen atom can do is make 1 bond, and then you can't really continue on. So hydrogen atoms go on the outside. Carbon always gets 4 bonds. People sometimes say organic is one of the hardest courses in chemistry. Honestly, guys, if you can count to 4, you can do organic chemistry. Carbon always gets 4 bonds. Okay, now, the types of compounds we're going to talk about the most in this chapter are called alkanes. The alkanes, those are compounds that only contain 2 elements, carbon and hydrogen. Trust me, a lot of organic chemicals contain more than carbon and hydrogen. A lot of organic chemicals contain nitrogen, oxygen, sulfur, phosphorus, all kinds of interesting things. But the simplest of all the organic compounds only contain 2 elements, carbon and hydrogen. And if you only have single bonds, so you only have carbon and hydrogen, you only have single bonds, you are classified as an alkane. So one of your simpler alkanes here is butane. This would be the stuff that's in a butane lighter. It's got the formula C4H10. You've got your 4 carbon atoms. And if you count them up there, you see there's 10 hydrogen atoms. Again, you notice the hydrogens have to be on the outer periphery. A friend of mine used to say organic structures are basically like a body. You have a skeleton made of carbon, and it's covered with a skin and the skin is made of hydrogen. And that's your basics of organic structure. Now, butane's a really small organic molecule. We deal with molecules that have 20, 30, 40, 50 carbon atoms all the time. So C4 is really a small molecule, and yet it's taking up a good chunk of this page, right? So we have to have ways of shorthanding this. What organic chemists do, we tend to break everything into chunks of CH3. Notice how that is a unit of CH3. So we'd call this thing, see, that is a unit of CH3, which is bonded. It's bonded over here to a unit of CH2, which is further bonded to another unit of CH2 and another unit of CH3. So, different ways of representing structures. You could do the full-on Lewis structure. Quite often doing the full-on Lewis structure is just, it takes up too much space on a page, so we shorthand it this way. I'll be honest, you don't even have to show these bonds going from carbon to carbon. I hope you all realize this bond is this bond going from carbon to carbon. That's this guy. So we don't have to show that. Sometimes people would write this as CH3, CH2, CH2, CH3. And again, knowing that hydrogens always go on the outer periphery, anybody who looks at this knows, hey, these hydrogens, all these hydrogens are out here on the outer periphery of the structure. Now, most organic chemists don't do this. We don't do this. When we draw butane, we draw it like this. We use what's called line angle notation. I'm going to give you a quick lesson on this because I think it's important stuff. It's not really even covered in your textbook, but if you take some biology classes, you're going to see line angle notation. Nobody's going to explain it to you. They're just going to assume you know what it means. So anyway, no, this will not be on the final. This is one topic they don't put on the final. If you had to draw butane, your 4 carbon atoms in a row, right? Line angle notation, it would look like this. To any organic chemist in the world, this means C4H10. I know that can be a somewhat intimidating sort of shorthand, but here's the way this works. In line angle notation, anytime you have 2 lines come together at a sharp corner, you assume that must be a carbon atom. That right there, it must be a carbon atom. At the end of any line, if there's no other element drawn there, you assume that must be a carbon atom. So what this line angle notation is saying is, hey, there's a carbon, there's a carbon, there's a carbon, there's a carbon. 4 carbon atoms in a row. So 1, 2, 3, 4 in a row. 1, 2, 3, 4 in a row. Well, but what about the hydrogens, you might ask? Well, remember, carbon always gets 4 bonds. So if you're looking at this carbon atom, he only has 1 bond drawn to him. You can infer that the other 3 bonds must be going to hydrogen. This carbon atom has 2 bonds that are drawn to him. You could infer that the other 2 bonds must be going to the hydrogen. Same thing here. And same thing over here. So what you're seeing is this is a unit. This is a unit of CH3. This is your CH2. This guy here is CH2, and this guy here is CH3. That is line angle notation. Now, we've got a couple of exercises here on the next page where it wants you to translate these structures into line angle notation. Again, this material is not going to be on the final, so I'm not going to go into it very deeply, but real quickly, if you wanted to see how these worked, you could always look at the notes on the website where it has the answers. But for this one here, you have 1, 2, 3, 4 carbons in a row, so you put your pen down. As soon as my pen touches that paper, that's a carbon atom. That's 1, 2, 3, 4 carbons in a row. 1, 2, 3, 4. But wait, there's this thing. Oh, that would be CHEM. So that would be the line angle notation of this. This one's kind of interesting. It's 3 carbons in a row. 1, 2, 3. Do y'all see? 1, 2, 3. 1, 2, 3 carbons in a row. Hey, this carbon in the middle has a little carbon coming up there and one coming down there. Some people would just do this one as E. And again, one of the things I didn't mention, anytime lines cross, if there's no other element drawn there, there's no oxygen, there's no nitrogen drawn in there, you assume that must be a carbon atom. Notice this carbon atom is different in that he has no hydrogens. He has 4 bonds to him already. This one, if we had to draw it real quick, like that oxygen there is that oxygen, which is then bonded to that carbon, to this carbon, to this carbon. This carbon happens to have a double bond to oxygen. So I hope you're seeing how line angle notation works. Any elements that are not carbon, that are not hydrogen, you have to draw them in. You have to draw in anything that's not a carbon or a hydrogen. But carbons and hydrogens, you don't bother doing them. Again, you just assume at the end of a line, it's a carbon. So this CH3 here is right there at the end of that line. This CH3 is right there. This CH3 is right there. This CH2 is right there. I hope you're getting the idea of line angle. Again, you're not going to be tested on that, so I'm not going to do this second half of the exercise at the bottom of the page. We're going to move right along here. Okay, isomerism. Oh, one thing before we get into all this. The line angle notation. That line angle notation sometimes really bothers people when they start seeing it. Where did it go? Back to the previous page. So people look at the full-blown Lewis structure. You have 4 carbon atoms in a row. We tell you you could draw it this way. You could condense it even more and draw it this way, or you could draw it as strictly as a line angle. Some people really fight that initially. Hey, check this out. If I build the Lewis structure, if I build a model based on this Lewis structure, although the Lewis structure makes it looks like the 4 carbons line a straight line, there's my model of butane. Do the 4 carbons line a straight line? Heck no, the 4 carbon atoms, they zigzag. Just like in the line angle notation. It's maybe easier to see if I get rid of all the hydrogen atoms. Again, the hydrogen atoms, I hope you're starting to realize, are just They're kind of like the chump change of organic chemistry. They're those terminal atoms that are always on the outside of a structure. If we take those off, let's go ahead and rip our hydrogens off and just look at our carbon skeleton here. Suddenly you realize that line angle notation is pretty darn logical, isn't it? Do y'all see the line angle notation? You see the actual shape, the actual structure of the molecule? So don't get upset when you start seeing line angle notation. You will see it if you take some biology. You'll definitely see it if you stay in chemistry any longer. Next thing to talk about then is isomerism. Isomerism is an interesting and an easy to understand concept. If you have a certain number of building blocks, a certain number of atoms, you have so many carbon atoms, so many hydrogen atoms, and you got to build a structure. Quite often you can build the structure more than one way. So it's showing you here if you had C4H10, that's our butane, our 4 carbons in a row, these are C4H10. You know what? I don't have to put it together with the 4 carbons all being in a straight line. Again, they're not straight line, they're zigzag. I could have 3 of them hooked up in a straight line, and one of the carbons coming up off the middle. Guess what? This structure here has this formula C4H10. They're totally different chemical compounds. This stuff is a different chemical than this stuff. They happen to have the same molecular formula. They just happen to have different shapes. They're different structures. The concept here is real simple. If I gave you a set of building blocks, say bricks, roofing tiles, things like that, and told you to build a house. Some of you are going to build a nice traditional square house. Somebody's going to make it rectangular. Somebody's going to build their house 2-story, 1-story, but using the exact same number of bricks, the same number of building materials, you can build different shaped houses. Using the same number of atoms here, the same number of building materials, you can build different molecules. And in this particular instance, when you have the 4 in a row, it's like that. We'll leave the hydrogens off. The hydrogens just kind of clutter up the picture, but there's your carbon backbone for butane. This one here, where you have 3 atoms in a row, that would be like this guy, where you have 1, 2, 3 in a row, and then you have an extra carbon atom coming up off the top. So you can see that they're totally different shapes. They're going to behave totally differently. They're not the same chemical. So this one's butane. This one's actually an entirely different thing called methyl propane. So they're not the same thing. One of the things that's interesting about isomerism is as the number of carbon atoms goes up, the number of isomers possible goes up exponentially. So if you had, say, 1 extra carbon atom, C5H12, you could build 3 different structures. This one, or this one. I think it's by the time you get to something like C30H62, there's over 1 billion possible ways you can put that together. The gist of it is this: there's an essentially infinite number of chemical compounds that can be put together based on carbon atoms. Some people find that intimidating. They find the field of organic chemistry endless and scary. Other people find that wonderful. You can build an infinite number of different structures based on carbon atoms and hydrogen atoms. And if you start throwing in few other elements, an occasional nitrogen or an oxygen, wow, you can build so many different structures, and that's why organic chemistry is the largest field of chemistry. Last topic in this video, don't know how long we've been going. The last topic is going to be, how do you name these things? How do you name these organic structures? We're only going to scratch the surface. All we're going to talk about is how to name the simplest of compounds, and those are the alkanes. How do you name alkanes? Remember, an alkane means all you have is carbon and hydrogen, and you only have single bonds. So if all you have is carbon, all you have is hydrogen, and everything is a single bond, you're an alkane. Of course, there's much more complex compounds. There's things with double bonds, triple bonds. There's things with these other elements, oxygen and nitrogen. But how do you name the alkanes? It's based on the name of the first 10 so-called normal alkanes. When we say normal, it just means the carbons are hooked up one to the other. There's no branching. What's branching? For butane here. Here's butane, carbon to carbon to carbon to carbon. Oddly, they call that a linear alkane. I know it really zigzags, but it's called a linear or a normal alkane. Now, here I've got the 4 carbon atoms, and I have a linear chain of 1, 2, 3, but I have a branch point. I have this little growth, this little wart coming off of that second carbon atom there. That's a branched chain alkane. So how do you name these? Oh, well, if it's a linear alkane, the name's taken from this table. 1 carbon in a row is called methane. 2 carbons in a row, ethane. 3 in a row, propane. Propane is, of course, used if you live out in the mountains. You probably have a propane tank, and your furnace burns propane. Here in Albuquerque, when your furnace kicks on, it's probably burning methane. I'll be honest, guys, the alkanes, we always start by talking about alkanes, how to name them. To most organic chemists, alkanes are boring as all get out. What do humans use alkanes for? We burn them. Your car lives off of octane. The gasoline you pour in your car is mostly octane, C8H18. So the first 10 normal alkanes, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, that forms the basis of our naming system. So, if you have to name an alkane, you always look for the longest continuous chain. So what's the longest continuous chain? Let's take a look at a couple of examples. This example here, got 1, 2, 3, 4, 5, 6. Hey, I have 6 carbons in a row, and I have a little branch point. Since my longest continuous chain is 6 carbons in a row, when I go to name this, the very last part of the name is going to be hexane. So again, 6 carbons in a row is called hexane. I've got my 1, 2, 3, 4, 5, 6 in a row. But darn it, this compound is not hexane. It's hexane with this little wart hanging off the top. That little thing is referred to as a group. Some people get hung up on what is a group. Here's what a group is. If you're not part of the main chain, you're not part of the longest chain, what are you? You're a group. If you have a one carbon group, we call you a methyl group. So this isn't hexane, this is methylhexane. It's supposed to be one word, left a space there, but it's one word, methylhexane. Because this little guy is a one carbon group. So this is a methyl group. So this is methylhexane, but wait, there's more. We gotta say where this group lives. I think it's obvious to you that I could have put this methyl group on this carbon and it would be a different compound, right? So we have this rule. We take the longest continuous chain and we assign numbers to each of the carbon atoms. It's kind of like assigning individual addresses to houses in a block. So we'd call this carbon number in blue, carbon number 1. This is carbon number 2, carbon number 3, 4, 5, and carbon number 6. So it's not methylhexane, it's 2-methylhexane. The little 2 tells us which position on the chain that the group is. Now, you might have noticed I numbered my things from right to left. The rule is when you're numbering the longest chain, you number it so that the first appearance of a group gets the lowest possible number. If I had numbered it wrong, we'll do it the wrong way here in red. If I'd numbered it carbon number 1, 2, 3, 4, 5, 6, then I would have ended up calling it 5-methylhexane. That would be incorrect. So you don't number it that way. Why call it 5-methylhexane if you can call it 2? So you number it so that the first group that shows up, and here there's only one group, it's a methyl group. You number it so that the first group that shows up gets the smallest number. So this is 2-methylhexane. Now, let's take a look at the next example. It has some more intense groups on it. Longest continuous chain. Guys, this is a lot more complex than anything we'll give you on the final, but if you had to find the longest continuous chain, don't be naive. Don't say 1, 2, 3, 4, 5, 6. No, for this one, your longest continuous chain is going to be 9 in a row. I'll circle it here for you. Your longest continuous chain here is those 9 carbon atoms. Now, some people, when they first start organic, they get hung up on, what do you mean by longest continuous chain? Here's the answer. You look for a chain of carbon atoms and you pretend that you're a little bug. Pretend you're a ladybug. How many carbon atoms can you walk across? How many can you touch without ever going backwards? You can turn to your right, you can turn to your left, you can make all kinds of turns, you can just never backtrack. So if I was a little bug, I could start here, I could walk along and touch 1, 2, 3, 4, 5, 6, 7, 8, 9. I could touch 1, 2, 3, yeah. So that's 9 carbon atoms in a row forming a continuous chain. Now, when I go to number these, let's look for our groups. I've got this group, a 1 carbon group, that's a methyl group. I've got this, a 2 carbon group, that's an ethyl group. So this one's an ethyl. Ethyl group. When I go to number it, should I number it 1, 2, 3, 4, 5, 6? My first group, my first group shows up on carbon 6. Or should I number it 1, 2, 3? Hey, then my first group shows up in position 3. Hey, go for the smallest. So this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 carbons in a row. 9 carbons in a row is referred to as nonane. So this is going to be nonane. Well, it's actually going to be 4 ethyl, 3 methyl nonane. Why did I put the ethyl first? The rules. We got lots and lots of rules. The rules say list the groups alphabetically. So ethyl comes before methyl. So the name of this compound is 4 ethyl 3 methyl nonane. So that's the name that is assigned to this compound. I know it seems strange. You get good at this really quick. Trust me, on the final exam, you won't see anything as complicated as this. Maybe in the next video I'll give you one more example of these, and then we'll move on to some other material. So that's your crash introduction to organic chemistry.